Okay, I guess I'm back with you here for our lab session in our Bayesian PKPD modeling course. A couple of things to go through today. One, we'll go over a solution to the homework I assigned back on Monday, and certainly answer any questions that you may have after you might have attempted some variation on that. And in particular, I noticed I had a problem with one part of it here, and you might have had a similar one, so I'll mention that as we go. But the other thing I wanted to mention here is there's two things here. One is a course project, which for those who want to take the course for credit, we do have a course project. And the other is, I mentioned before, the midterm exam, which I'm still behind on getting together. I should hopefully have that together by hopefully by this weekend or so, so that you'd have access to it next week. And I guess that's also a thing to remember here. Reminder that there will be no lecture or lab session next week. But I will try and get the midterm exam and make that available to you, along with I'll post instructions about it on the course website and make sure that you get emails posted to you about it. Okay, in the meantime, let's talk about the course project. So again, one of the requirements for course credit is completion of a small modeling project. Actually, I thought I got rid of the word population, but that'll do. I was thinking of a small hierarchical modeling project, which may or may not fit under the heading of population. And that project represents 50% of the course grade. The project is due within 2 weeks of the final course lecture, so that would be, essentially by the beginning of 2011. Is what that amounts to. And if you have any questions about it, certainly both questions as far as the expectations and any questions you have about the specifics of your own project, certainly feel free to contact me. The requirements that I've got are relatively loose. The idea is for you to define your own project, but with some general guidelines. Choose what I say is either a real-world problem or a simulated data set that's consistent with a real-world problem, shall we say, and choose one that's suitable for modeling with a Bayesian hierarchical model. For example, it could be like a population PK or PD model. In the interest of maintaining reasonable run times, and of course I guess we all have our own definition what reasonable is, but what I'll say here is just try to restrict the scale of the problem to something where the analysis can be completed within less than 2 hours. So if it looks like you're getting into a somewhat larger scale, I recommend maybe what you turn in something that's based upon a subset of the data or something like that in order to keep the run times down to something fairly reasonable. I want you to develop and implement a suitable model using WinBUGS. So we want you to use a WinBUGS framework. Use R for your data management, for launching WinBUGS, and for analyzing the MCMC simulations that WinBUGS produces. So all that should be done in R, much like the examples we've done in class. Summarize your methods, your results, and your conclusions, and include supporting figures and tables in a brief report. The report format that's preferred would be PDF. I can probably live with other things, but that would be my preferred one. And your results should include suitable model evaluation plots, such as the posterior predictive checks that we've discussed in class. You should discuss the results, and part of that discussion should include a discussion of the assumptions that are inherent in your analysis, And one particular thing I mentioned, because it is unique to the Bayesian framework, is include some discussion of the rationale for your prior distribution that you've used in your model. And then finally include supplemental files, things like data files, R scripts, and WinBUGS model files. I guess probably the preferred way to do all of this would be to package the whole thing up into a zip file that when I unzip it will give me the report as well as the supporting files. So that's pretty much the story on that. Again, if you've got any questions about that, feel free to ask. I guess I'll stop now for a second and see if there's any immediate questions about it. Okay, nothing so far. These pages that I just showed you are in a revised slide set that I posted to the course website not too long before the course. I think I posted it maybe half an hour ago. So you may not have seen an email about it yet. In fact, you wouldn't have seen an email now that I think of it. I never did send out a notice about it. I'll do that. But anyway, it is posted on the website. In addition, posted to the website is a worked solution to the homework that I'm about to go over here. So let's talk about that homework. Actually, maybe let's scoot up to some of the things we were talking about last time. Now, the homework here was kind of to have you combine a couple elements, a couple of modeling elements that we discussed in the last lecture. And where do we go here? One was to embellish a bit upon what I talked about in terms of implementing interindividual variance matrices other than just the simple single full block matrix for all of the parameters. And so so what I was suggesting is taking the example I did, which I think I called hands-on 3 PBIIV, I think, for partial block IIV. And for that, you'll end up with a bivariate normal distribution for clearance and V1, but in addition, unlike the example I gave, rather than having Q and V2 as not having any unexplained interindividual variability, suggested including that as a separate bivariate normal block in there. So we have bivariate normal for clearance and V1, bivariate normal for Q and V2, and then a univariate normal for Ka in there. So that was one component. And then the other component is where we talked about the missing covariate values, covariate data, and recall I gave you an example where I implemented a model that in effect did a simultaneous with the analysis. It did an imputation or a multiple imputation on body weight in there, and that, so I recommended incorporating that. So it's, hopefully I've recalled this correctly, since we sort of made the assignment a bit extemporaneously, but I believe that was the whole component, the whole element in that. So let's wander down to Windows World here and see one approach to that. Okay, and as I say, I just not too long ago posted this on the course website, so you have access to it there. Okay, let's start by firing up our WinBUGS here, And let me grab the model file. Okay, come on, let me get, there we go. Okay. So what I did is I used the previous example I had. Recall one of the examples, let's see, it was this one right here that was ME2 hands-on 3 PBIIV. So I used that as my template that I built on to create this one, which I called PBIIV MISSCOV here for missing covariate at the end. The first parts of this is before. We're going to go on a loop that goes over all of our individuals, where we deal with our interindividual variability here. The first part is the same as before. It's almost the same as before. This is almost the same as the other one where we did the partial block variance model here. The only thing that's different here is because of what we're going to be doing with doing the imputation for weight. I have this thing here, instead of using body weight here all by its having an object that's its body weight, I've got a matrix that has both weight and age in it, but I pick off the first column, which contains the body weight. So that part's a bit different in that sense. But in the end here, this term right here is just returning the body weight for the jth individual in here. Okay, and I've got my bivariate normal for the logs of clearance and volume of distribution in there. So that's more or less almost the same as what we did before. The difference here is I introduce another one for Q and V2, and you'll notice I just used the previous block of code right here as a template, and basically every place where you saw CLV1 in the previous block of statements there, I replace it with QV2 as part of that. And there where I had clearance hat before, I've now got Q hat here, and where I had V1 hat, I now have V2 hat here. So otherwise it's the same as before. The dependence upon body weight we had assumed was the same particular sort of allometric scaling strategies as we did for clearance and volume of distribution, so that doesn't change. So, and then finally we have our univariate normal here for the absorption rate constant. So there's not much different there. There's little bits of differences down here where I finally convert to my theta matrix here. Before, you would have just seen on the right hand side, you would have just seen log Q in that line, and you would have seen log V2 on this one. Well, now I've got this matrix here that's been created by the call to the bivariate normal, so I have to pick off the appropriate element of that. So I pick off the first column corresponds to my theta 2, which has to correspond to Q, and I pick off the second one to assign to our theta 4 here, which is supposed to correspond to V2. So it's just a matter of, again, keeping the bookkeeping straight on what belongs to what, because the thetas that are going to be passed to the two-compartment model function have to be in the correct order. Let's see, is there anything in that stuff that's... Oh, I did do one other thing that's different. And this was just more or less cleaning up the code a little bit in a sense. If you recall, in the previous case, I passed to WinBUGS the entire vector of weight values. So there was a separate weight value for every observation, but I actually only used the baseline value in each case. So if you recall, in the previous code you were working with, where I have start J, or where I have J here, I had, I'll type it here so you see it. I had start J there. What I've done instead is done the equivalent. Instead of picking off the baseline weight and age within BUGS, instead I picked it off within R and only passed one value of weight and age for each individual, since we never actually use any of the other values in the model anyway. So that's why you just see a J here. And this is probably a good point to pull up the R script so you see where that's happening. Okay, the first parts of the R script are no different other than the fact that the model name has changed to correspond to the one I'm using here. So let's scroll on down to, where are we here? Okay, here's where it happens, right here. Okay, oh, there's another thing that's going to happen that I'll have to explain too, but the key part I wanted to explain now is where I'm picking off by specifying start here. If you look at the previous one, you'll see that this would have just been blank for the row index. Instead, I put start in here, which is going to pick off the baseline value for each one of the subjects from both the weight and the age columns of the data set. So I'm only going to pull in the values that correspond to the baseline values here and pass those instead of passing that entire vector to it. So that takes care of that part. Now there's one other difference. One thing that you might notice here is instead of having weight age here for that matrix of weight and age values, I have log of weight and age, and chose, instead of modeling weight and age as bivariate normal, I've modeled weight and age as bivariate log normal. One of the reasons for this, well, I guess there's sort of two reasons. It makes some logical sense because weight and age both have to be non-negative. So using log normal makes sense from that point of view. But the other reason was even more pragmatic than that, and that's when I tried to run it using a bivariate normal, I ran into some numerical traps within WinBUGS that I was having difficulty resolving. And they all had something to do with taking the log of a negative number somewhere in the sampler having to do with a multivariate normal. So after trying various things, I said, well, let's try this, since I thought about doing it anyway, and model weight and age as bivariate log normal. And so far anyway, I still haven't actually run this all the way to completion, but I've run it far enough well beyond where I ran into the numerical problems with the bivariate normal. So I ended up going with log normal. So that's why you see here a log transformation being done. You can see the log on the right-hand side here. And so it's actually passing the logs of weight and age to BUGS instead of just weight and age. So let's go back to the BUGS over here. So let's see. So we've taken care of, so we've got our weight age thing here. So a lot of the rest of this again is the same. Of course, I had to change the call for our posterior predictions too. So you see all over again this log QV2 pred here to generate or to simulate individual level values of those. A lot of the rest of this is same old, same old. We've got our calls to the BUGSModelLibrary function here going on. Let's see, we do the conversion from the amounts that are calculated by the BUGSModelLibrary function to concentration. That's the same as before. And again, what's different here occurs right here, which is where we're going to do the multiple imputation. Basically, at this point we're modeling a relationship between weight and age, and we're going to use that model relationship to impute the missing values of weight in this case. So you can see what I've done here. Now this was the old code taken from that ME2 hands-on 3 MISSCOV example where I used a bivariate normal for weight and age. What I've done instead now is done a bivariate normal for the log of weight and age. And that's what you see reflected in this line. So you can see the left-hand side then represents our what is data at this point. So in the cases where we have observed values for weight and age, they serve as data, and this serves as a likelihood function then for estimating the means and the variance matrix for this bivariate log normal describing weight and age. Actually, again, it's weight and age by gender. There's actually two separate distributions being generated here, one for males, one for females in here. And then I threw in the one additional step to calculate weight and age from the log transform values in the next step. Now, and again, just remind you, in the cases where either weight or age are missing in this, this step, instead of functioning like a likelihood for those cases, will function like a simulator, and will simulate new values, essentially simulate a posterior distribution for weight or age. Now in this case I only had missing values for weight, so it would only be simulating them for body weight for the cases where we have no observed value in there. So we'd get the log of weight as part of that, and then we'd convert that just to weight down in the next step. Let's see, the only other things that happen then that are different would be, let's see, a couple of things here. We have to introduce priors for a few things. So we've got our prior on our omega, in our variance matrix for Q and V2, or it's actually the inverse of that covariance matrix. We've got a prior, again, in terms of a Wishart distribution with 2 degrees of freedom on that. Let's see, what else do we introduce here? Well, somewhere we see. I guess it doesn't change what we put down for the priors on the individual means here for like our log V2 hat, log Q hat. That doesn't change anywhere in here. And then finally, it's a little bit different here, where we deal with, again, our weight and age model because of the log transformation here. So I've now put a essentially uninformative or very weakly informative priors on both weight and age at this step, and I actually didn't do anything. I left the one for the variance matrix, or the inverse of that variance matrix, the same as I did when I was doing the bivariate normal. Downside here, I haven't run this to completion. It does take, I'm not sure exactly how long it'll take, but it looks like it's going to take better than an hour to run to completion. And I, having struggled a bit with those numerical errors, I didn't get it done in time to show you. I'll post, I guess, when I get that done and can do so, I'll post a final solution that also shows the results. Right now, all you've got is the code that I'm showing you here. I'm trying to think if there was anything else different in the R code. Not much. Of course, the things like the let's see here. We have to introduce here I introduced the parameter associated with the prior distribution for the variance matrix for Q and V2. Well, I had to recall I artificially introduced the missing weight values right here, and I had, and I had that log transformation, so the names change to say log weight age. And let's see, anything else in here? Of course, I've got I've got initial estimates here for any of the new components that I've added here. Again, like the inverse of the variance matrix for Q and V2 again shows up there. Had to change the name again for my because it's going to be log weight age hat, and put in numbers that are appropriate for the log transform values. Oh, I see one other thing I did that was in an attempt to deal with the numerical problems I had that didn't solve it, but it's probably worth mentioning to you as a strategy, that when you do run into numerical errors with bugs, there's some things that can sometimes help. By the way, for those of you who haven't encountered them yet, though I suspect most of you have, when you get numerical errors, what happens in bugs is you'll get a new window will appear in the bugs GUI, and it will usually say something like trap something or other, usually a number, and then it might also give you the first line or two may give you at least some useful information, like attempting to take log of a negative number or something like that in there. Unfortunately, a lot of the trap messages are pretty cryptic and hard to figure out. But anyway, you'll get something called a trap. So you'll often hear me refer to those error messages as traps because of the terminology used by bugs. Sometimes what can help is if you run into numerical problems that you're having difficulty figuring out, but let's say you've provided initial estimates maybe only for the main parameters in here, but you haven't provided them for any of the random effects. Sometimes providing initial estimates for the random effects, particularly in cases where you're using very weakly informative priors, can help, because sometimes what will happen is bugs will come up with some strange initial estimates on its own, which can cause those numerical errors. So what you'll see I've done here is for a number of the random variables in the model that I wouldn't always include initial estimates, I have anyway to try and get the chains to start in reasonable places and avoid some of the numerical errors that may come from producing rather strange initial estimates. So you can see what I've done here. You'll see I've got log weight age, and if you look at the code here, what I've done is, now you only want to provide initial estimates for random variables. Now in the case where weight or age are observed, those are not random variables at that point. Those are observed data, and you have to view those essentially as deterministic in the context of this analysis. But in the cases where it's missing, those are treated as random variables. They're random variables you're going to be simulating within the model. So I only want to provide initial estimates for the missing ones. So you can see here I say if else, and over here it says is NA for log weight age. So basically it takes any elements in that log weight age data item inside the bugs data. If that's missing, it will then put an initial estimate in there, in this case of the log of 70 kilograms in there. Otherwise, it's just going to put an NA value, which is what you want it to do in the case where in the data set it's an observed value. And then what I've done otherwise here is for all of our random effects on our model parameters, so that's clearance, V1, Q, V2, and KA, you can see lines here which are providing initial estimates for the individual level values of those parameters. So that's what's going on here, where I'm saying log clearance V1, I'm passing in a matrix. It's going to have two columns, and in this case it's one, and it's going to have a number of rows equal to the number of individuals. And the first row is going to, or the first column is going to consist of all values equal to log 10. which is going to serve as my initial estimate for clearance, and the second column is all going to be log 70, which is my initial estimate for V1 in here. And you'll notice that those numbers match up with what I used as my central tendency in the population means up here on top. So here, let's see the log 10 and the log 70 right here. And then I do the same thing for Q and V2, and then finally for KA in here. So again, sometimes that can improve the MCMC performance, or at least help avoid some numerical traps along the way. So I should probably do it as a matter of course, but often when I first run these, I don't include those kinds of initial estimates. But again, it can be helpful. And in the extreme, it can also sometimes be helpful even for the dependent variables. So for instance, in our case where we're looking at our dependent variable is the log of the observed concentrations. If some of those are missing values, again, sometimes it can also pay off to assign initial estimates to those in cases where you run into numerical problems. Let's see, anything else new? I don't think so. Now, as I say, I will post the actual results of this once I finally get them. Actually curtailed a run in here so that we could actually do the class without half my computer being used for that purpose here. But I'll go ahead and run it afterwards. Let's see. I do have one question I see popped up. Let's see. Oh, okay. The question had to do with could I explain the trick I use for creating start and end inside R. So let's go down to that where I'm setting up the data set we passed to BUGS. Oops. Going too fast here. Where'd it go? Okay, here it is. Okay. So the main trick occurs right in the lines right here. So again, to remind you what I'm trying to do with start. So start is going, so we've got this, for the various model or various data components here, like our dependent variable and some of the other things like time, amount, rate, and so on. We've got each of those as a vector equal to the total number of observations. And just like in a non-mem data set, I've stacked stacked one subject on top of another in my data set in here, and within a subject they're time ordered. Okay, so they're in the order in which the events have occurred for that subject. And make sure I get this articulated well here. What I want for what I'm going to be doing inside the BUGS model, I want to know the index that corresponds to a given subject's first observation within that whole vector of observations. So start is going to then be a vector. It's going to be a vector that has a length equal to the number of individuals. Each element in start is going to tell me what the data index is for the corresponding individual. So, for instance, the ith value, the ith element of start will contain the index for the first data item for the ith individual in here. The way I create that is, first of all, you'll see this component right here on the right-hand side where I say not duplicated, and you can see I've got X data $ID, ID being my subject identifier in here. And duplicated, if we ignore the not part at the beginning, duplicated is a function that will return false when a given data value is first encountered, and it will be true for any subsequent values equal to that. So In our case, what is going to happen if I was to use, say, duplicated X data ID, it's going to return false for the first value, for the first time it encounters that particular ID value, and it will be true for all the subsequent values of that are equal to that one. And if I say not duplicated, it's going to flip that so that it'll only be true for the first observation for that individual, and it will be false for every subsequent ones. So I'll get this big vector then of trues and falses, where the trues are at the index corresponding to the first observation for each individual. Then what I'm doing here, okay, I take a vector which is just going to be values going from 1 to the number of observations, and I'm going to then subset that, as is shown on here, where I put the indexes here, and what it's going to return is only the values going from 1 to n obs that correspond to trues on this side. In other words, it's only going to return a number coming out of this vector for the first observations, which in this case will correspond to the actual index of that observation. So that's my start, and then end comes from that pretty easily right here, because the start value for, actually maybe I better explain some elements in here. When I say start -1 like this, what that does is it takes the start vector but throws out the first record. In other words, it's going to or the first element. So this is going to be start 2 start 2 and above. Start 1 is no longer there. And basically that's because the index for the first observation for the second subject is 1 more than the last observation for the first subject. And that's why I take those values of start, beginning from the second subject forward, and subtract 1 from it. So now that's going to tell me where the last observation is for every subject except the last one. But then the index for the last observation in the last subject is simply the last observation in the data set. And that's why I tack on the n-obs on the end of that. So that's the start and the end. Let's see, any other questions? Well, I wish it were brilliant. I'm sure I stole it from somebody else, so it was their brilliance. But then I've also been accused of being overly terse in some of my code in R, so feel free to criticize on that basis. Okay. Well, let's see. I'm not seeing anything crop up. We're probably going to go ahead and cut it fairly short. So if you want, you can go ahead and download this, or if you prefer, you can wait until the I post the results in addition to the code I've got here. The exam, I'll also post that once I've got that ready. My intention is to use the quiz taking capabilities of the course website as the means for giving the course, but this is my first time using it, and if I get too frustrated with it, I may end up just sending you a document that you can then mark up and then email back. But right now I'm hoping to be able to use the quiz taking capabilities of the website. But our course is small enough that the only big advantage to using Well, there's, I guess, two advantages. With the course website, it gives you a way of sort of automating the process of doing a re-examination, and it also allows it to be essentially graded instantly and give you feedback instantly. But our courses, our group is fairly small, so it's not that much labor for me to do it, to correct them manually. It's just that you won't get your feedback as quickly. Okay, well, if there's no more questions, I guess I'm going to be leaving you, and other than the additional messages you'll get from me, we won't actually have another course until, what is the date of that? Let's see, it's going to be, I guess that's not until November 8th is when I'll be joining you again. So until then, I guess I'll see you. I'm going to be off to England for a week then. And talk to you then. Bye.